Welcome to the Sleepy Science Facts, your place to relax and discover the mysteries of the universe in the most peaceful way possible. Tonight, we're embarking on a calming journey to explore one of the most enigmatic and fascinating objects in the cosmos: black holes. Imagine a place where time slows, space curves, and the normal rules of reality seem to disappear. As we drift deeper into the unknown, we'll uncover some of the most fascinating facts about black holes. So, if you're ready to unwind, let your mind settle and join us in unraveling the incredible nature of these cosmic giants. But before we dive in, don't forget to like and subscribe to the Sleepy Science Facts so you can drift off to even more relaxing, mind-bending topics every week. Now, let's see what lies beyond the edge of our understanding. When we think of black holes, we often imagine mysterious voids, dark and silent. But these cosmic objects are far from empty. They are filled with an invisible force so powerful, it warps time and space itself. But to truly understand them, we need to start at the most fundamental concept of all: gravity. We've all heard that gravity is the force that pulls things together. But what if gravity isn't a force at all? What if instead it's something far more profound, something that bends the very fabric of space and time? This might sound strange, but this revolutionary idea started to take shape in the early 20th century, when Albert Einstein unveiled his theory of general relativity. Einstein proposed that space and time are not two separate things. They are interconnected, forming a unified fabric that can be distorted by mass and energy. This idea changed everything we thought we knew about the universe. In this theory, gravity is not the invisible force we once imagined pulling objects toward each other. Instead, gravity is the result of space-time itself being curved by massive objects. This curvature influences the motion of all things, not because they are being pulled, but because the space they move through is bent. To visualize this, imagine a stretched sheet, like a trampoline. If you place a marble on a flat sheet, it stays still. But if you place a heavy ball in the center, the sheet dips. Now, if you roll a marble across this sheet, it will move toward the heavier object, not because the ball is pulling it, but because the surface beneath it is curved. This is the essence of gravity in Einstein's view. Mass curves space-time, and objects move along the path of least resistance through this curved space. On Earth, we experience this gravity every day as our planet moves around the sun, not because the sun pulls us in, but because the sun's mass bends space in such a way that we are simply following the curve of space-time. And this same concept applies at the most extreme points in the universe, like at the very heart of a black hole. But what happens when too much mass is packed into too small a space? This is where black holes come into play. When mass is squeezed to an extreme degree, space-time doesn't just curve, it folds in on itself. The fabric of space becomes so steep that nothing, not even light, can escape its pull. This is what defines a black hole. A region in space where the curvature of space-time is so intense that everything, light, matter, even time itself, is drawn inward. But despite the name, black holes are not empty spaces. In fact, they are full of mass, compressed into an incredibly dense region. Imagine trying to fit the mass of a star into a space smaller than the size of a city. This compression warps the space around it, creating a region where everything is pulled in with no way out. At the very edge of this region lies what's known as the event horizon. This is the point of no return, the boundary beyond which nothing can escape, not even light. But it's not a physical surface. It's more like the edge of visibility itself. From outside the event horizon, signals can still escape, but once crossed, no message can return. If you were floating just above the event horizon, you might still be able to send a signal. But if you were to step just a little further, all paths would lead inward. The shape of space-time itself would prevent you from returning. The event horizon doesn't block you. It simply alters the structure of space and time so fundamentally that there's no direction left to go but down. Imagine, if you will, a spaceship drifting toward the edge of a black hole. It's approaching the event horizon, the point of no return, the boundary between the known universe and the mysterious uncharted void beyond. From the perspective of an observer watching from a distance, time seems to slow down for the spaceship as it nears the event horizon. It appears to freeze, suspended at the edge, never quite crossing the line. The light from the ship stretches, becoming redder and more distant until it fades away into nothingness. This is the strange effect of gravity on time, a phenomenon that Einstein's theory of relativity predicted. Time itself slows down as you get closer to the event horizon, the boundary of the black hole. But this is not the experience of the spaceship's crew. From their perspective, time continues normally. Their clocks tick, their instruments measure, and they pass the event horizon without feeling anything extraordinary. No jolt, no flash of light. It's a smooth transition, like drifting through a veil into a deeper part of the universe. It is one of the great mysteries of black holes. Why do observers at different locations experience time differently? For those outside the event horizon, time seems to come to a standstill. But for those inside, everything continues, as though the universe hasn't changed at all. The event horizon marks the point where the fabric of space and time becomes so distorted that it bends our perception of reality itself. At this boundary, light behaves in strange ways. It still travels at the speed of light, but is trapped. As it gets closer to the event horizon, light is stretched out, its wavelength becoming longer. This is known as redshift. The closer an object gets to the event horizon, the more extreme the redshift becomes. Eventually, the light becomes invisible to the outside world, as if the black hole were swallowing it up, keeping everything within its grasp. But the event horizon isn't just about light and time. It also marks a dramatic shift in the very nature of space itself. The geometry of space beyond the event horizon becomes radically different from what we experience in the rest of the universe. From the outside, the black hole seems to have no distinguishing features. It's a dark, invisible sphere. But once you pass the event horizon, the geometry of space inside bends so completely that all paths lead toward the singularity, the heart of the black hole. What lies beyond the event horizon? No one knows for certain, but this region is defined by the complete collapse of the rules of physics as we understand them. Once inside, the fabric of space-time folds in on itself, leading to a singularity, a point where the density of matter becomes infinite, and the laws of physics as we know them cease to function. It's a place where the curvature of space-time becomes so extreme that we can no longer predict what happens. All paths, all possible futures, lead inward. There is no escape. But here's the strange thing. As far as we can tell, nothing physical seems to happen at the event horizon itself. There's no visible surface, no wall, no shock. In fact, if you were to pass through it, You might not even notice. The experience is smooth, uneventful, almost serene. The event horizon isn't a physical boundary in the traditional sense. It's a point of no return in the geometry of space-time itself. So, what happens when something falls into a black hole? From the outside, it seems as though the object is frozen in time. It never quite crosses the event horizon. It just appears to hover there, lost in a state of suspended animation. The image of the object becomes stretched out, dimmer, and eventually disappears from view. But to the object itself, the experience is entirely different. It crosses the event horizon without hesitation, without resistance, as though stepping through a doorway into a new, deeper part of the universe. Inside the event horizon, there is no turning back. The paths of light and matter all lead toward the singularity, a point of infinite curvature at the heart of the black hole. But this singularity is not a physical object, not a point we can observe or interact with. It is a breakdown in the fabric of space-time, a place where our current theories fail to describe what happens. The density of matter becomes infinite, and the curvature of space becomes unbounded. In fact, the singularity itself is not something we can truly know in any meaningful way. It lies beyond our ability to observe, hidden behind the event horizon. What we know about it comes only from the behavior of the space around it. As objects fall into the black hole, they are stretched and distorted by the immense tidal forces. Light and matter are twisted and drawn inward, moving toward the singularity without any possibility of escape. But this idea of the singularity is not without its challenges. It's a place where the known laws of physics break down. The equations of general relativity cannot describe what happens at the singularity. Some physicists believe that this means our understanding of space and time is incomplete, that there is a deeper, more fundamental theory yet to be discovered. Perhaps it is quantum mechanics that will offer the answers, providing a more complete description of black holes and the singularity at their heart. Until we develop a theory of quantum gravity, the singularity will remain a mystery, a place where our current understanding of the universe fails. And yet, even with all the unknowns, the singularity is a crucial part of the black hole. It shapes the structure of the black hole from within, defining its very nature, even though it remains forever hidden from view. The singularity lies at the heart of every black hole, but it is far more than just a point in space. It represents the ultimate breakdown of our understanding of the universe. At the singularity, space and time cease to behave as we expect. The very laws of physics begin to fail, and we are left with a mystery that even the most advanced theories cannot fully explain. To understand the singularity, we must first grasp how it forms. Imagine a collapsing star, its core growing denser and denser until it can no longer support itself against the force of gravity. At some point, this core reaches a critical threshold. The pressure and density become so immense that the star's core begins to collapse in on itself, pulling everything inward, creating a singularity. The singularity is not a physical object, but a point where space and time become infinitely warped. As the star's mass collapses, the curvature of space-time becomes so extreme that nothing, not even light, can escape. Time itself slows, and everything that falls into the black hole is drawn inexorably toward this point of infinite density. At the singularity, the equations of general relativity break down. This means that our current understanding of gravity and space-time cannot describe what happens inside a black hole. The laws of physics, as we know them, fail. We can no longer predict the future behavior of matter and energy. All paths lead to the same place, the singularity. But we cannot fully comprehend what happens when we reach it. Many scientists believe that the singularity marks the boundary of our understanding. It's a place where current theories of gravity and space-time break apart, revealing a need for a new theory of quantum gravity. Quantum mechanics, which describes the behavior of particles at the smallest scales, has not yet been reconciled with general relativity, which governs the universe at the largest scales. The search for a unified theory, one that can explain both the microscopic and macroscopic worlds, is one of the great challenges of modern physics. There is, however, an intriguing possibility that quantum mechanics might hold the key to unlocking the mystery of the singularity. Some theorists suggest that quantum gravity might allow us to see through the singularity and resolve the breakdown of space-time that occurs there. Theoretical models, such as string theory or loop quantum gravity, offer a glimpse into how space-time might behave under these extreme conditions. These ideas suggest that the singularity may not be a point at all, but rather a quantum foam, a region of space where quantum fluctuations prevent the complete collapse of matter. For now, though, the singularity remains a place where our current understanding of physics breaks down. It is a place of infinite curvature, where the rules we know cease to apply. The search for answers continues, but for now, the singularity remains beyond our reach. But what happens when something crosses the event horizon and falls toward the singularity? The journey inward is not immediate. As an object falls toward the black hole, it undergoes extreme distortions. The closer it gets to the event horizon, the more these distortions increase. Light stretches, objects are stretched and compressed, and time itself begins to slow. If you were to observe an object falling toward a black hole from a distance, you would notice that as it approached the event horizon, it seemed to slow down. The object would appear to freeze in place, suspended at the edge of the black hole, never quite crossing the event horizon. The closer it got, the slower it would appear to move. This is due to the intense gravitational field near the black hole, which stretches the light emitted by the object, making it appear redder and redder. Eventually, the object would fade from view altogether as its light becomes stretched beyond the visible spectrum. From the perspective of the object itself, however, the experience would be quite different. As it falls closer to the event horizon, time would seem to move normally. Its instruments would continue to tick, its clocks would continue to run, and it would continue to fall inward. The passage through the event horizon would be smooth, almost imperceptible. The object would not feel any sudden jolt or shock, even as it passes the point where not even light can escape. Once past the event horizon, however, there is no turning back. The geometry of space itself has been altered so profoundly that all paths lead toward the singularity. There is no direction left to move except inward. This marks the point of no return. The object has crossed into a realm where time and space behave in ways we cannot yet fully understand. At the singularity, the object would encounter the breakdown of the laws of physics. The curvature of space-time becomes so extreme that the known laws of general relativity no longer apply. The density of matter becomes infinite, and time itself begins to behave in unpredictable ways. But beyond that, we can only speculate. What happens to matter when it reaches the singularity? Does it vanish? Is it compressed into a new form? We do not yet know. But one thing is certain. The singularity represents the ultimate mystery of black holes. It is the point where our understanding of the universe breaks down, and it is here that physicists hope to find the answers to some of the deepest questions about the nature of space, time, and gravity. As we continue our journey through the black hole, we come to a fundamental question. What happens to space and time as we approach the singularity? What does it mean for the fabric of the universe itself to be so distorted? In the normal world, space and time behave in predictable ways. We can move through space, traveling in straight lines, and time passes steadily. But near a black hole, everything changes. Space and time become interwoven, and the very shape of reality itself begins to bend in ways that are difficult to comprehend. Imagine for a moment that you are falling toward a black hole. As you approach it, the first thing you would notice is the way space itself begins to warp. At the event horizon, the space around you starts to stretch, curving inward as if it were being sucked into a vortex. But this isn't just space stretching. Time is stretching as well. From the perspective of an outside observer, time seems to slow down as you approach the event horizon. Your movements appear to freeze in place, and the light you emit is redshifted, stretched to longer wavelengths until you disappear from view. This is the first sign that time near a black hole behaves differently from what we experience in the everyday world. Time does not flow the same way for everyone. For an outside observer, time slows down near the event horizon. But for you, the person falling in, time continues to move normally. In fact, as you cross the event horizon and continue toward the singularity, time seems to stretch and compress in strange ways. But from your perspective, everything feels just like it did before. You are falling, yes, but your clock is ticking and your instruments are working normally. The way that time behaves near a black hole is a direct result of the warping of space-time. In general relativity, time and space are not separate entities, but are woven together into a single four-dimensional fabric. When this fabric is curved by massive objects like stars or black holes, it causes time to behave differently. In the case of a black hole, the curvature of space-time becomes so extreme that time begins to stretch toward infinity as you approach the event horizon. From a mathematical perspective, this warping of time is described by something called the light cone. The light cone is a representation of the possible directions that light can travel through space and time. In normal conditions, the light cone is symmetrical, allowing light to move in all directions from the past to the future. But near a black hole, the light cone becomes distorted. As you approach the event horizon, the cone tilts inward so that all paths lead toward the singularity. No matter where you go, no matter how hard you try to resist, you will always be drawn inward. This is a dramatic departure from how we think of time and space in the everyday world. Time near a black hole is no longer a steady, ticking progression. Instead, it becomes a direction that you can't avoid. The closer you get to the event horizon, the more time itself seems to slow, until it almost comes to a complete standstill. The structure of space-time is no longer familiar, and it becomes impossible to navigate in the same way we do in the more typical regions of the universe. This change in the nature of time also leads to what is known as time dilation. As you fall toward the event horizon, time seems to slow down for an outside observer. But for you, the traveler, time continues as usual. To you, everything feels normal. But from the perspective of someone far away, you appear to slow down more and more until you seem to freeze in place. In reality, you're still moving forward, but because of the warping of space-time, your time is stretched out. But time dilation is just one of the strange effects that occur near a black hole. The curvature of space itself becomes more and more extreme as you get closer to the event horizon. Imagine a flat plane stretching out before you. Normally, you could move freely across this plane, going in any direction you choose. But as you approach a black hole, the plane begins to curve, and the direction you can move in becomes limited. All roads lead inward toward the singularity. There are no other paths to take. This is the profound effect of the black hole on the fabric of space and time. At the event horizon, the curvature becomes so steep that nothing can escape. Even light, which normally travels at the fastest speed in the universe, is unable to break free. It is trapped within the black hole's grasp, forever spiraling inward, and for anything that crosses the event horizon, there is no turning back. The future is set. There are no other options, no other paths to take. The singularity awaits. But what happens to time inside the black hole itself? Once you pass the event horizon, you are no longer an observer from the outside world. You are now inside the black hole, where the geometry of space-time is so altered that time no longer behaves as we understand it. The rules of physics, as we know them, begin to break down. The concepts of space and time become intertwined in such a way that it's impossible to tell where one ends and the other begins. Inside the event horizon, space and time are not just distorted, they are fundamentally altered. Space is stretched and compressed, and the very idea of direction becomes meaningless. There is no way to distinguish between the future and the past. Everything that falls into a black hole is inevitably drawn toward the singularity, where the curvature of space-time becomes infinite. But even within this strange and distorted region, we must remember that the singularity itself is a place beyond our understanding. It is a place where the known laws of physics fail and the limits of our comprehension are reached. For now, it remains a mystery. The search for answers continues as we seek to understand the nature of space, time, and the fundamental structure of the universe itself. So, as we near the singularity, we find that our understanding of space and time is stretched to its limits. The black hole, a region where time is warped, space is bent, and the laws of physics break down, forces us to confront the mysteries of the universe in ways we never could have imagined. It is a place where the very fabric of reality is torn, revealing the deepest truths about the nature of existence itself. As we drift deeper into the black hole's embrace, we encounter another fascinating feature: the accretion disk. This is not a solid object, but rather a swirling, turbulent disk of gas, dust, and other matter that has been drawn toward the black hole. As this material spirals inward, it heats up, becoming incredibly bright and energetic, and emits light across the entire electromagnetic spectrum. The accretion disk forms as matter falls toward the black hole. As it gets closer, the material is pulled by the intense gravity of the black hole, and its angular momentum causes it to spiral inward, rotating faster and faster. This spiral motion leads to friction between the particles in the disk, generating enormous amounts of heat. The closer the material gets to the black hole, the hotter it becomes, reaching temperatures high enough to emit X-rays and ultraviolet radiation. But it's not just the heat that makes the accretion disk so interesting. It also represents a dynamic, constantly changing system, where matter is caught in a dance with the black hole. The material in the disk is not falling in uniformly. Instead, it experiences powerful forces that twist, compress, and stretch the gas and dust. These forces cause the material to behave erratically, creating turbulence and magnetic fields that add to the complexity of the disk. One of the most extraordinary aspects of the accretion disk is the way it produces energy. As matter falls toward the black hole, it loses angular momentum. This loss of energy leads to the material speeding up and heating up, creating a spectacular glow that can outshine entire galaxies. The process of accretion, the gradual accumulation of material, is one of the brightest phenomena in the universe. But not all of the material in the accretion disk falls directly into the black hole. Some of it is ejected in powerful jets of radiation and particles that shoot out from the poles of the black hole at nearly the speed of light. These jets are not coming from the black hole itself, but from the outer regions of the accretion disk, where the magnetic fields and intense rotational forces help to launch the material outward. These jets can extend vast distances, sometimes reaching far beyond the galaxy itself. They are a dramatic and energetic feature of black holes, and they play a key role in shaping the environment around the black hole. The jets are a form of energy release, allowing the black hole to speak to the universe in the only way it can, through the emission of radiation and particles. The process of accretion is far from simple. It's a violent and chaotic process where matter is torn apart, heated to unimaginable temperatures, and flung outward in jets of energy. The entire system is constantly in motion, with matter constantly moving toward the black hole, losing energy and being heated to incredible levels. This dance of matter and energy is a beautiful and complex interaction that continues for as long as the black hole remains active. But despite all the energy being generated, the black hole itself remains invisible. We cannot see the black hole directly because no light can escape from inside the event horizon. But we can observe the effects of the black hole through the light emitted by the accretion disk. By studying this light, astronomers can infer the presence of black holes and learn more about their properties. The accretion disk serves as a kind of shadow for the black hole. It provides us with a glimpse into the black hole's behavior, allowing us to study its mass, spin, and energy output. The disk also serves as a laboratory for studying the extreme physics that govern black holes. By observing how matter behaves in the accretion disk, scientists can test theories of general relativity, quantum mechanics, and high-energy astrophysics. But the accretion disk is just the beginning. The black hole's gravitational pull has far-reaching effects on its surroundings. It doesn't just devour matter, it shapes the galaxy around it. The energy released by the accretion disk and the jets can influence the formation of stars, the behavior of nearby gas clouds, and even the overall structure of the galaxy itself. In fact, supermassive black holes, located at the centers of galaxies, have a profound effect on their host galaxies. The energy and material expelled by the black hole can heat up the surrounding gas, preventing it from collapsing into new stars. This process, called feedback, can regulate the growth of the galaxy. Without the energy from the black hole, the galaxy might grow too quickly, forming new stars at an unsustainable rate. The interaction between the black hole and its galaxy is a complex and delicate balance. The black hole, though hidden in the darkness, plays a crucial role in the life of the galaxy. It can suppress star formation, create turbulence in the gas, and even shape the overall structure of the galaxy. In this way, black holes are not just passive objects in the center of galaxies, they are active participants in the evolution of the cosmos. The accretion disk, with its swirling clouds of gas and dust, is a testament to the immense power of black holes. It is a place where matter is stretched, compressed, and heated to extreme temperatures, creating some of the brightest and most energetic phenomena in the universe. But it is also a place of mystery, where the laws of physics are tested to their limits. As we continue to study the accretion disk, we learn more about the nature of black holes and the profound impact they have on the universe around them. As we continue our journey through the black hole, we are drawn into one of the most profound and surprising aspects of these cosmic giants, their ability to shape the universe around them. Far from being passive, black holes are active players in the drama of the cosmos, influencing the formation of galaxies, stars, and even the flow of energy throughout the universe. At the very center of most galaxies lies a supermassive black hole, often millions or even billions of times the mass of our sun. These black holes are the gravitational hearts of their galaxies, and their influence extends far beyond their immediate surroundings. Despite the fact that black holes themselves are invisible, their gravitational pull is felt across vast distances, shaping the motion of stars, the behavior of gas, and the very structure of the galaxy. In many galaxies, the black hole is not a dormant object, it is active, feeding on the gas, dust, and stars that fall into its grasp. As matter spirals inward in the accretion disk, it generates an enormous amount of energy, emitting light across the electromagnetic spectrum. This energy is so powerful that it can outshine entire galaxies. The light emitted by the accretion disk, combined with the jets of particles launched from the poles of the black hole, creates an incredibly energetic environment. But the power of black holes is not just about energy. Their influence extends even further, regulating the growth of galaxies themselves. As matter falls into the black hole, the energy released by the accretion disk and the jets can heat up the surrounding gas. This process, called feedback, can prevent the gas from collapsing and forming new stars. Without this feedback, galaxies could grow too rapidly, forming stars at an unsustainable rate. In this way, black holes serve as cosmic regulators, helping to balance the growth of galaxies and their star-forming activity. Feedback from black holes can also have a direct effect on the interstellar medium, the gas and dust that fills the space between stars. The energy released by the black hole can push the gas away, creating bubbles and cavities in the medium. This alters the dynamics of the galaxy, preventing gas from collapsing to form new stars and regulating the rate of star formation. Through this process, black holes not only shape the galaxy they inhabit, but also influence the evolution of the entire cosmos. This feedback mechanism also plays a role in the formation of supermassive black holes themselves. As black holes grow by accreting matter, they can influence their surroundings, drawing in more gas and dust, feeding the black hole even further. The growth of the black hole is not a solitary process. It is intertwined with the growth of the galaxy around it. Together, the black hole and the galaxy evolve in tandem, with the black hole acting as a central force that shapes the galaxy's development. One of the most striking examples of this is seen in the phenomenon of active galactic nuclei, AGNs, where the black hole at the center of the galaxy is feeding on large amounts of gas. As the gas spirals inward, it heats up and emits enormous amounts of radiation. This radiation can be so bright that it outshines the combined light of all the stars in the galaxy. These AGNs are some of the most energetic and powerful objects in the universe, and they provide us with a window into the workings of black holes and their role in shaping the cosmos. Even more extraordinary are the jets of particles that are launched from the poles of some black holes. These jets can extend for millions of light years, blasting through space with speeds approaching the speed of light. These jets are not emitted from inside the black hole, but from the outer regions of the accretion disk, where magnetic fields twist and accelerate particles to incredible velocities. The jets can influence the surrounding environment, interacting with nearby gas clouds, shaping the structure of the galaxy, and even affecting the formation of new stars. These jets are not just powerful, they are also dynamic. As they travel through space, they carry with them information about the black hole's properties, its mass, spin, and orientation. By studying the jets, astronomers can learn more about the inner workings of black holes, their behavior, and their influence on the surrounding universe. While black holes may seem like isolated objects, they are in fact deeply connected to the rest of the universe. Their energy, gravity, and magnetic fields stretch across vast distances, shaping the galaxies they inhabit and influencing the larger scale structure of the cosmos. They are cosmic engines that drive the evolution of galaxies, regulate the rate of star formation, and even power some of the most energetic phenomena in the universe, such as quasars and gamma-ray bursts. The black hole's role in the cosmos is far more than just that of a silent observer. It is an active force, influencing everything around it, from the formation of stars to the behavior of galaxies. As we continue to study these cosmic giants, we learn more about the interconnectedness of the universe, how everything, from the tiniest particles to the largest structures, is shaped by the same fundamental forces. But despite all the knowledge we have gained, there is still much we do not understand. The true nature of the black hole's singularity, the relationship between quantum mechanics and general relativity, and the ultimate fate of the information that falls into a black hole. These remain some of the deepest mysteries in science. And yet, in our quest to understand black holes, we are uncovering not only the secrets of these cosmic giants, but also the fundamental laws that govern the universe itself. The story of black holes is not just a tale of destruction. It is a story of creation, of forces that shape the very fabric of space and time. As we continue to explore these fascinating objects, we are not just looking into the darkness of the cosmos. We are peering into the very heart of the universe, discovering the underlying forces that make everything possible. As we drift further into the cosmic journey of black holes, we must turn our attention to their life cycle. These enigmatic objects are not static. They evolve over time, growing and changing as they interact with their surroundings. From their formation to their eventual end, black holes follow a remarkable path, a cycle that reveals just how dynamic these cosmic giants truly are. The birth of a black hole begins with the death of a star. When a massive star reaches the end of its life, it can no longer sustain the nuclear fusion at its core. The balance between gravity pulling inward and the pressure from nuclear reactions pushing outward collapses. and the star implodes under its own weight. This collapse can trigger a supernova, a brilliant explosion that outshines an entire galaxy for a brief moment, scattering heavy elements across the universe. But for the most massive stars, the supernova is just the beginning. If the remaining core has enough mass, typically several times that of the Sun, it will continue to collapse. Eventually, the pressure from even the densest forms of matter, such as neutrons, will not be enough to halt the collapse. The core will collapse into an infinitesimally small point, a singularity, at the heart of the black hole. This is the birth of a stellar mass black hole, an object with an immense gravitational pull capable of bending the fabric of space-time itself. Once formed, a black hole begins its journey, slowly drawing in matter from its surroundings. This matter may come from nearby stars, gas clouds, or even from other black holes. As it falls into the black hole, it is not swallowed all at once. Instead, the material forms an accretion disk, swirling around the black hole in a tight, hot spiral. As the matter moves inward, it is heated to incredibly high temperatures, emitting energy in the form of light and radiation. The black hole's growth doesn't stop there. Over time, it continues to accrete more and more matter, growing larger and more powerful. The process is not always smooth. However, black holes can grow in spurts, rapidly devouring large amounts of matter in what are known as feeding frenzies. These events are often marked by the release of intense radiation, as the black hole's gravity pulls matter in at a tremendous rate. In some cases, the energy release can be so powerful that it outshines entire galaxies. As a black hole grows, it can also merge with other black holes. When two black holes come close enough, their immense gravitational fields begin to influence each other. They spiral toward one another, slowly losing energy in the form of gravitational waves, ripples in space-time that carry away the energy of the system. Eventually, the two black holes collide, merging into a single, more massive black hole. These mergers are not only fascinating from a scientific perspective, but they also provide us with a unique way to observe black holes. Gravitational waves, first detected in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO, allow us to hear the merging of black holes, offering a new window into the hidden realms of the universe. By studying these waves, scientists can learn more about the properties of black holes, such as their mass, spin, and how they evolve over time. After a black hole has grown and merged, it continues to shape the universe around it. The energy emitted by the accretion disk, combined with the jets of particles shot from the poles of the black hole, can influence the entire galaxy in which it resides. This energy can regulate star formation, heat up gas clouds, and even cause massive outflows of material, sometimes preventing further star formation and altering the structure of the galaxy itself. Despite their immense power and influence, black holes are not eternal. Eventually, they begin to lose mass. This process is called Hawking radiation, named after the legendary physicist Stephen Hawking, who first proposed it in 1974. According to Hawking's theory, black holes are not perfectly black. They can emit radiation as a result of quantum effects near the event horizon. Over time, this radiation causes the black hole to lose energy and mass, slowly shrinking it. However, this process takes an incredibly long time. For large black holes, such as supermassive black holes at the centers of galaxies, the time required for them to evaporate completely is much longer than the current age of the universe. For all practical purposes, These black holes are effectively eternal. Yet, eventually, even the largest black holes may fade away, leaving behind only the faintest traces of their existence. As black holes approach the end of their life cycle, they become even more fascinating. In the final stages of their evaporation, the radiation they emit becomes more intense, and their mass decreases at an accelerated rate. This process, known as black hole evaporation, may eventually result in the complete disappearance of the black hole, leaving no trace behind. But what happens to all the information that falls into a black hole? This is one of the most profound and unresolved questions in modern physics. According to general relativity, once something crosses the event horizon, it is lost forever. But quantum mechanics suggests that information cannot be destroyed. This paradox, known as the information paradox, has sparked intense debate among physicists, leading to new ideas about how information might be preserved or even recovered from a black hole. One theory proposes that the information is encoded on the event horizon itself, a concept known as holography. According to this idea, the information about the objects that fall into a black hole is not lost, but rather stored in a two-dimensional form on the boundary of the black hole. While this idea remains theoretical, it has provided a new avenue for research, offering hope that we may one day solve the riddle of what happens to information in a black hole. Another possibility is that black holes could serve as gateways to other regions of space and time. Some theories propose that the singularity inside a black hole may not be a point of infinite density, but rather a bridge to another part of the universe, or even another universe entirely. These wormholes could, in theory, connect distant regions of space, allowing for faster-than-light travel or even time travel. While there is no direct evidence for the existence of wormholes, the idea remains a fascinating possibility. In the end, the life cycle of a black hole is one of constant change and mystery. From their birth in the collapse of massive stars to their eventual evaporation, black holes evolve in ways that challenge our understanding of physics. They are both destroyers and creators, shaping the galaxies they inhabit, influencing the flow of energy, and providing us with clues about the fundamental laws of the universe. As we continue to explore the nature of black holes, we now turn our attention to one of the most profound questions in all of cosmology. What role do black holes play in the ultimate fate of the universe? Black holes are not isolated objects. They are deeply intertwined with the evolution of galaxies, stars, and the very fabric of space-time itself. Their influence reaches far beyond their immediate surroundings, and their ultimate fate may help determine the long-term future of the cosmos. Understanding black holes is not just about understanding these enigmatic objects. It's about understanding the end of time itself. To begin, let's consider what happens when a black hole evaporates. As we discussed earlier, black holes are not eternal. Over incredibly long timescales, they slowly lose mass due to a process known as Hawking radiation. This radiation, first proposed by physicist Stephen Hawking in 1974, suggests that black holes are not completely black. Instead, they emit a faint glow due to quantum effects near their event horizon. Over vast periods of time, this radiation causes the black hole to lose energy and thus mass. For small black holes, this process could lead to their eventual disappearance. However, for large black holes, such as supermassive black holes at the centers of galaxies, The process of evaporation takes longer than the current age of the universe. These massive black holes may persist for billions of years before they ever evaporate completely. But what happens when a black hole eventually disappears? Will it simply vanish, leaving no trace behind? Or could the process of evaporation hold some deeper mystery? Some scientists believe that the information about the objects that fall into a black hole is not truly lost, but is instead encoded in some form of radiation. This is where the information paradox comes into play. According to quantum mechanics, information can never be destroyed. Yet, according to general relativity, information that crosses the event horizon of a black hole is lost forever. This contradiction has led to the idea that black holes may eventually reveal this lost information as they evaporate. The idea that black holes might leak information as they shrink is a key element of the modern understanding of black hole physics. Theories such as the holographic principle suggest that the information about anything that falls into a black hole is stored not inside the black hole itself, but at its event horizon, encoded on the two-dimensional surface of the black hole. As the black hole evaporates, the information could slowly be released in the form of Hawking radiation, offering a potential solution to the information paradox. But the ultimate fate of black holes isn't just a theoretical mystery. It is deeply connected to the fate of the entire universe. As black holes evaporate and disappear, they slowly diminish the mass and energy in the cosmos. Some scientists believe that over an incredibly long period of time, all the black holes in the universe will eventually evaporate, leaving behind a dark, empty universe with no more light or matter. This scenario is known as the heat death of the universe, a state where everything has reached maximum entropy and the universe becomes a cold, lifeless void. But there is another possibility. Some theories propose that black holes could play a role in the creation of new universes. This idea is based on the concept of eternal inflation, which suggests that new regions of space-time could be continually generated by the energy and matter inside black holes. In this model, when a black hole evaporates, it may create a new baby universe, a small pocket of space-time that continues to expand and evolve, potentially giving rise to new stars, galaxies, and black holes. This process of cosmic rebirth is still highly speculative, but it offers an intriguing possibility. The black holes might not be the end of the universe, but rather the beginning of something new. Instead of disappearing into nothingness, the death of a black hole could mark the birth of a new universe, with its own set of physical laws and properties. These ideas are still very much in the realm of theoretical physics, and much more research is needed before we can fully understand the long-term fate of black holes and their role in the universe's ultimate destiny. But what is clear is that black holes are not just the end points of stars, but active players in the ongoing evolution of the cosmos. As black holes continue to grow, merge, and evaporate, they shape the structure of galaxies, influence the flow of energy, and affect the very fabric of space-time. They may be the key to unlocking the deepest mysteries of the universe. From the nature of time and space to the possibility of new universes emerging from the death of old ones, the eventual fate of the universe remains one of the greatest unsolved mysteries in science. Will it end in darkness, with all black holes evaporating into nothing? Or could it be that black holes are not the end, but the beginning of something new, a cycle of cosmic rebirth that continues forever? These are questions that we may not be able to answer in our lifetime. But as we study black holes, we are uncovering clues about the ultimate fate of the universe itself. The more we learn, the closer we come to understanding the true nature of space, time, and existence. In the end, black holes are not just cosmic oddities. They are the final frontier of our understanding of the universe. The place where the laws of physics break down, where time and space are stretched and twisted, and where the deepest mysteries of existence await us. As we continue to unravel the mysteries of black holes, it's worth considering how far we've come in our ability to study these enigmatic objects. For centuries, black holes were purely theoretical, objects that existed only in the minds of mathematicians and physicists. But today, thanks to groundbreaking advances in technology and observational techniques, we are beginning to peer deeper into the universe and catch glimpses of these hidden giants. The first step in our understanding of black holes came from Albert Einstein's theory of general relativity, which predicted that black holes should exist in regions of space where gravity is so intense that not even light can escape. This theory revolutionized our understanding of gravity, showing that space and time are not fixed entities, but dynamic, flexible constructs that can bend and stretch in response to mass and energy. But for a long time, the idea of black holes remained speculative, something that couldn't be directly observed. It wasn't until the 1960s and 1970s that astronomers began to gather evidence for the existence of black holes. The first clue came from the discovery of quasars, bright, energetic objects at the centers of distant galaxies. These objects emitted vast amounts of radiation, far more than could be explained by the light of stars alone. As scientists investigated further, they realized that quasars were likely powered by supermassive black holes at the centers of galaxies, objects that were drawing in vast amounts of gas and energy. The next step came in 1971, when astronomers detected the first black hole candidate, Cygnus X1, located in our own galaxy. Cygnus X1 is a binary system where a massive star orbits an invisible object, the star's movement, as it was pulled by the unseen object's gravity, provided evidence that it was being influenced by something incredibly dense and compact, a black hole. The discovery of Cygnus X1 was a major milestone, as it provided the first direct evidence that black holes could exist in nature. In the years since, scientists have discovered many more black hole candidates, both stellar mass black holes and supermassive black holes at the centers of galaxies. But how do we detect black holes, given that no light can escape from within them? The answer lies in observing their influence on the surrounding environment. One of the most powerful tools for studying black holes is the detection of gravitational waves, ripples in space-time caused by the acceleration of massive objects. When two black holes merge, they send out gravitational waves that travel across the universe. In 2015, scientists made a historic breakthrough when the Laser Interferometer Gravitational Wave Observatory, LIGO, detected the first gravitational wave from the merger of two black holes. This discovery not only confirmed a key prediction of Einstein's theory of general relativity, but also opened a new era of astrophysical research. Gravitational waves provide a way to study black holes directly, offering a new window into their properties and behavior. But gravitational waves are not the only way we can study black holes. Another important technique is the observation of the accretion disks that form around black holes. These disks are made up of gas and dust that is being drawn toward the black hole's gravitational pull. As this material spirals inward, it heats up and emits radiation, which we can observe using telescopes. The radiation from the accretion disk provides a wealth of information about the black hole's mass, spin, and the conditions around it. In some cases, we can even observe the motion of stars and gas near the event horizon, giving us a glimpse into the immense forces at work. One of the most stunning pieces of evidence for black holes came in 2019 when the Event Horizon Telescope EHT collaboration released the first ever image of a black hole. Using a global network of radio telescopes, the EHT captured an image of the supermassive black hole at the center of the galaxy M87. This image, which shows a glowing ring of gas surrounding the black hole's event horizon, marked a monumental achievement in the field of astronomy. It provided a direct visual confirmation of the existence of black holes and gave us our first clear look at their surroundings. Yet, even with all the progress we've made, there is still so much we don't know about black holes. The biggest challenge we face is understanding what happens inside the event horizon. Once an object crosses the event horizon, it is effectively cut off from the rest of the universe. No information can escape, and the laws of physics as we know them no longer apply. The singularity at the heart of the black hole is a region where our current theories break down, and we have no way of knowing what happens there. This is where the quest for a unified theory of quantum gravity becomes so important. General relativity, which describes the behavior of gravity on large scales, and quantum mechanics, which governs the behavior of particles at the smallest scales, are currently incompatible. To truly understand black holes, we need a theory that can unify these two frameworks, a theory that can describe both the immense forces at work in a black hole and the quantum effects that occur at its heart. Some scientists believe that a complete theory of quantum gravity will offer answers to some of the most profound questions about black holes, such as the nature of the singularity and the fate of information that falls into a black hole. One promising candidate is string theory, which posits that the fundamental particles of the universe are not point-like objects, but rather tiny, vibrating strings. If string theory is correct, it could provide a framework for understanding the behavior of black holes at the quantum level, potentially resolving the information paradox and offering insights into the true nature of space-time. But string theory is just one of many approaches to quantum gravity. Other theories, such as loop quantum gravity and causal dynamical triangulation, offer alternative views of how space-time behaves at the smallest scales. These theories suggest that space-time itself is not continuous, but rather is made up of discrete units. Understanding how these theories apply to black holes could be the key to unlocking the mysteries of the universe. Even though we've made tremendous progress in understanding black holes, we are still at the beginning of this journey. There are so many unanswered questions. What exactly happens at the singularity? Can black holes truly serve as gateways to other universes? How does the information paradox get resolved? What role do black holes play in the evolution of the cosmos? These are questions that may take decades or even centuries to answer. But every discovery we make brings us one step closer to understanding the deepest mysteries of the universe. As we continue to study black holes, we are not just learning about these cosmic giants, we are also learning about the fundamental nature of reality itself. the very fabric of space and time, and the forces that govern the universe. As we come to the final chapter of our journey into the heart of black holes, we reach the ultimate question that has captivated scientists, philosophers, and stargazers for centuries. What lies beyond the black hole? Is it simply a place of nothingness, a point where everything disappears? Or could black holes hold the key to unlocking new dimensions of space and time? Perhaps even the mysteries of other universes? While we have learned much about black holes, from their formation to their role in shaping galaxies and stars, there is still so much we don't understand about what happens inside them. The event horizon marks the boundary beyond which we cannot see or retrieve information. Anything that crosses this threshold seems to be lost forever, swallowed up by the singularity at the heart of the black hole. Yet, despite this, the idea that black holes might contain answers to some of the deepest mysteries of physics and the universe continues to intrigue us. The concept of what lies beyond the black hole is one that challenges our very understanding of reality. If we cannot observe or measure anything that falls into a black hole, how can we ever know what happens to it? Does the matter and energy that fall into the black hole simply disappear? Or is something more profound happening? Could black holes serve as gateways to other parts of the universe, or even other universes entirely? One intriguing possibility is that black holes could act as wormholes, tunnels or bridges that connect different regions of space and time. This idea comes from solutions to Einstein's equations of general relativity, which suggest that the geometry of space-time could allow for the existence of these shortcuts, which we call wormholes. If black holes are connected to other parts of the universe through wormholes, then they might not be the ultimate end of the matter they consume, but rather the beginning of something new. In theory, a wormhole could connect two distant regions of space, allowing matter or even light to travel from one place to another instantaneously. Some scientists believe that black holes could be portals to these wormholes, offering a pathway to distant parts of the cosmos, or even to other universes entirely. While this idea is highly speculative and remains unproven, it remains a tantalizing possibility. Another fascinating theory involves the multiverse, the idea that our universe is just one of many, existing alongside countless others. Some versions of the multiverse theory suggest that black holes could serve as the entry points to other universes. If this is true, then each black hole could lead to an entirely new and separate universe, with its own set of physical laws and constants. This means that black holes could be the cosmic bridges that connect different universes, allowing for the creation of new realities and dimensions. While these ideas are still very much in the realm of theoretical physics, they push the boundaries of our understanding of space, time, and the universe itself. What we do know for certain is that black holes are not just destructive forces, but powerful catalysts for change in the cosmos. They are the engines of creation and transformation, shaping the galaxies around them and holding secrets that could revolutionize our understanding of the universe. In recent years, new developments in physics have provided us with additional clues about what might lie beyond the black hole. Theories of quantum gravity, which aim to merge general relativity with quantum mechanics, suggest that the singularity at the heart of a black hole may not be the end of everything, as once thought. Instead, it may be the beginning of a new set of physical laws, ones that we are only beginning to understand. One such theory is the concept of black hole complementarity, which suggests that information that falls into a black hole is not lost, but rather encoded on the event horizon itself. This idea proposes that the information is not destroyed at the singularity, but is instead preserved in a two-dimensional form, akin to a hologram. If this theory proves to be correct, it would resolve one of the most perplexing puzzles in modern physics, the so-called information paradox, and open the door to a new way of thinking about the relationship between gravity, quantum mechanics, and the fabric of space and time. Another groundbreaking concept is the idea of quantum foam at the Planck scale, which describes space-time at the smallest possible scale. According to some theories, black holes could be a key part of the quantum foam, where space and time are no longer continuous but instead made up of tiny, discrete units. If black holes are part of this quantum structure, they may hold the key to understanding how space and time behave at the smallest scales and how the universe emerged from the Big Bang. But even with all these exciting theories, we are still far from fully understanding what lies beyond the black hole. Our current knowledge is limited by the fact that we cannot observe the interior of a black hole directly. We can only study its effects on the surrounding space, the way it bends light, the way it distorts time, and the way it interacts with matter. As our technology continues to improve, we may one day be able to peer even closer into the heart of these cosmic giants, uncovering more secrets about their true nature. For now, the mystery of what lies beyond the black hole remains one of the greatest challenges in science. But this uncertainty is part of what makes the study of black holes so thrilling. As we explore these strange and fascinating objects, we are not just studying the endpoints of stars or the remnants of massive objects. We are peering into the very nature of the universe itself, into the fabric of reality, and into the mysteries that lie beyond the limits of our current understanding. And with that, we've reached the end of our journey through the mysterious world of black holes. From their formation to their role in shaping the universe, black holes remain one of the most fascinating and enigmatic phenomena in science. As we continue to explore the cosmos, there is still so much more to discover. Thank you for joining us on this peaceful exploration of the universe. If you enjoyed this journey and found it as captivating as we did, please consider liking this video and subscribing to the Sleepy Science Facts for more relaxing, informative content. By subscribing, you'll be the first to experience more deep dives into the wonders of the cosmos, all designed to help you unwind and drift into a world of discovery. If you have any thoughts or questions about black holes or any other cosmic mysteries, feel free to leave a comment below. We'd love to hear from you. Until next time, sleep well and keep dreaming of the stars.